Welcome you all in the ninth lecture of Electronics Measurement and Instrumentation. In this lecture, I will discuss different type of DC and AC bridges. So, this is the outline of my lecture. First, I will discuss the basics of bridge circuit, then DC bridges, that is Wheatstone bridge and Calvin bridge, and after that the general equation of for AC bridge, and then what are the different errors caused in AC bridges and application of AC bridges, and then simple capacitance comparison bridge and inductance comparison bridge. So, what is bridge circuit? Basically, bridge circuit is made up of 4 impedances like shown in figure. So, the 4 impedances are in closed loop circuit and they are connected in the form shown in figure. So, there are 4 nodes A, B, C, D. So, in 2 different nodes, 2 opposite nodes, source is applied, and the remaining 2 nodes, in between remaining 2 nodes, the detector circuit is used. The supply may be DC or AC, that depends upon the type of bridge, and detector circuit may we can use a simple galvanometer or we can use the vibrational galvanometer, we can use microphone and the tuned circuit, that depend upon the requirement of the bridge circuit. So, in this bridge when we apply a supply voltage, then a current will flow, and the detector circuit, that is suppose we are using simple galvanometer, then that galvanometer shows some deflection. At that time the bridge is known as in unbalanced condition. So, to make the bridge balanced condition, we have to vary either Z1, Z2, Z3, any one of the impedance, and the bridge is known in the balanced condition when there is no current through the detector. So, the condition that when there is no current through the detector means that the potential at the voltage at D point and the voltage at B point is same. When there is voltage at B and D point is same, so at that time because there is no potential difference, no current will flow through the detector, and so it will not deflect. So, that is known as the balance condition of the bridge. So, for the balancing conditions, here 2 conditions are required. The detector current ID should be 0 and the potential difference between the detector node should be 0. When the detector node potential difference is 0, the ID current will be 0. So, this is the classification of bridge circuit. So, we can classify bridge circuit into 2 types, one is DC bridge, another is AC bridge. In DC bridge generally we use Wheatstone bridge, Calvin bridge, mega ohm bridge. In AC bridge we can measure inductance, capacitance or the frequency. So, in inductance there are 3 type of bridge I will discuss, that is Maxwell bridge, Hayes bridge and Ohm's bridge. For the measurement of capacitance I will discuss the sharing bridge, and for the measurement of frequency Wien bridge is used. So, Wheatstone bridge I have already discussed in last lecture when this bridge is measured for the medium resistance. So, we know that under balance condition means there is no current through the galvanometer, it means ki the voltage at C and D point is same. So, when voltage at C and D point is same means the voltage drop across A and C is equivalent to the voltage drop across A and D. Similarly, the voltage drop across C and B is equivalent to the voltage drop across D and B. So, we can see in this equation that since there is potential difference, there is no potential difference between C and D. So, we know that I1 R1 is equal to I2 R2. Similarly, since there is no current through galvanometer, so it means the I1 current will flow through R3 also. So, I1 and I3 is same. So, I1 I3 is same and it is equivalent to the total voltage V divided by the total resistance, that is R1 R3. Similarly, we can find out I2 and I4. I2 is equal to I4 is equal to V by R2 by R1. When we simplify these equations, we will get R1 is equal to R2 into R3 by R4. So, when the bridge is in balance condition, it means the product of the opposite arms are equal. It means the product of opposite arm means R1 into R4 is equivalent to R3 into R2 in this condition. So, it means ki when we are using any bridge, the product of the impedances of the opposite arms are equal. So, these are the application of Wheatstone bridge. Wheatstone bridge is used for the generally for the measurement of resistance. Apart from this, we can use the Wheatstone bridge for the measurement of temperature, pressure, strains, etc. So, for the measurement of temperature, we can see in the diagram, we can use a Wheatstone bridge for the measurement of temperature. So, temperature measurement is done by thermocouple or the thermistor. We know, suppose we want to measure the temperature of any oven or the furnace, then we have to place transducers, that is thermistor or thermocouple. So, these transducers, thermistor or thermocouple basically converts the change in the temperature into change in resistance. So, if we apply a supply voltage there, then it will change the change in voltage. So, that change in voltage is measured by the bridge. So, this in this bridge, when we want to measure the temperature, first of all we have to keep this bridge into under balance condition. So, when bridge is in balance condition, then we will apply the temperature here. We will put the this thermistor or thermocouple in the oven or anywhere where we want to measure the temperature. So, because of this temperature difference, the resistance will change, and because of the change of resistance, this bridge will go into unbalanced condition. When the bridge will go into unbalanced condition, then there is a voltage difference between x and y point, and we can measure this change in temperature, because this change in voltage is very low in value, suppose in microvolt or in millivolt. So, we have to use an amplifier circuit to amplify that signal, and this way we can measure the temperature of the any furnace or any oven. Here we can calibrate this meter in terms of temperature. So, it will directly read the temperature. Similarly, we can use the Wheatstone bridge for the strain measurement. So, strain means, suppose we want to measure a heavy truck, loaded truck. So, to measure that loaded truck, generally the strain gauges are used, and strain gauges are in the form of load cells, means 4 strain gauges are used. Here in first figure, we have seen that there is one strain gauge, and that one strain gauge means if there is a pressure is applied there or the weight is applied there, and due to that pressure, force or strain, the resistance of that strain gauge will change, and the resistance will change from 30 ohm to 3000 ohm, 3 kilo ohm. So, because of the change of this resistance due to the pressure on the strain gauge, so that change in resistance will unbalance the bridge, and because of that unbalance, a voltage difference between x and y will created, and that will be checked by the voltmeter. And again, if we calibrate the voltmeter in terms of strain or the weight of the device in terms of weight, then it will directly measure the weight of that particular place. Generally, the voltage difference produced by the strain gauge is very low, and the second thing is, if there is any environmental change affect that measurement, so it will not counted by in this diagram. So, what we will do, we are using 4 strain gauges in form of bridge and 2 strain gauges. As we know, the product of the opposite arms is same. So, here we are using 4 strain gauges, in which 2 strain gauges are used in the form of where it will get tension, and the other 2 are used in the form of compression. So, when weight is applied, 2 strain gauges or the pressure is applied, 2 strain gauges will form a tension and 2 form the compression. So, because of that, the voltage difference will be high, and that can be measured in terms of weight. So, we can calibrate the voltmeter, and we can measure the weight or the force or the strain by this particular configuration. So, what is the basic problem in the Wheatstone bridge, that if we want to measure a very low resistance, then the wires of the Wheatstone bridge, the resistance that wires have, that is also included in that measurement. So, to measure a low resistance, we are using Kelvin bridge. So, in Kelvin bridge we can see that there is the problem is that if R x is of low value, so we will place a low value resistance of R 3. So, now the condition here is that this R 2 by R 1 should be equivalent to the R M P by R N P. So, when this condition is fulfilled, this Kelvin bridge by which this Kelvin bridge we can measure the very low resistance. So, Kelvin bridge is generally used to measure the resistance. So, what we will do, suppose our bridge, this galvanometer terminal is connected to M terminal one time and then N terminal, then we have to place it in between these two, so that it can cancel the resistance that is offered by the terminal of the bridge. So, in Kelvin bridge, the first condition that has to met, that is R N P by R M P is equivalent to R 1 by R 2. So, now we can add in this equation plus 1 both the side. So, it will be R N P plus R M P by R M P is equal to R 1 plus R 2 by R 2. Now, if we consider this bridge and this bridge is in balance condition, suppose we have to put this galvanometer's terminal at M. So, it means R 2 by R x plus R N P is equivalent to R 1 by R 3. So, it means R 2 into R x plus R y is equivalent to R 1 into R 3. In second condition, if this is terminal is connected to N terminal, so what will happen? R 2 into R x is equivalent to R 1 into R 3 plus R y. So, by solving these two equations, we will get this R M P is equal to R 2 into R y by R 1 plus R 2. Similarly, we will get R N P is equal to R 1 R y by R 1 plus R 2. So, now the balance, under the balance condition, we can see that R x plus R M P into R 2, R x plus R N P into R 2 is equal to R 1 R 3 plus R M P. So, by solving this equation, we will get that R x is equal to R 1 R 3 by R 2. So, there is no term of R N P or R M P when we are solving it. So, hence the effect of resistance of connecting lead from M to N has been removed by connecting the galvanometer to the intermediate position at P. So, now this is all about DC bridge. Now, in AC bridge, in DC bridge we are using a DC source and we are using a simple galvanometer. So, simple galvanometer can detect whether there is a current through this terminal or not. So, whether the bridge is in balance condition or unbalanced condition, that a simple galvanometer can show. But in case of AC bridge, we are using AC source, and so for the AC source we need different type of detector circuits. So, we can use microphone or we can use any other things, that is tunable amplifier to for the detector purpose. So, in AC bridge we can measure the unknown inductance and capacitance. Generally it is used for the measurement of the inductance, capacitance and maybe the frequency of any source. So, again it has 4 arms, 4 node, and this AC bridge consists of impedances, whereas in DC bridge only the resistances are used. And when we need to measure a component with very low frequency, then we can use simply power line of our normal power line, that is of 50 hertz, and if we want to measure at high frequency, then we will use in electronics oscillators. So, general balance equation for AC bridge. So, as we know, the AC bridge are made up of impedances. So, in impedances, again this is shown, there is impedances, and in detector, at the place of detector, we will use the tunable amplifier or the microphone, and here the AC source is applied. So, again when bridge is in balance condition, it means no current will flow through the detector circuit. So, it means again here E1 is equivalent to E3 and E2 is equivalent to E4, means the current I1 is equivalent to I3 current and I2 is equivalent to I4 current. So, and since there is no current through the detector in the balance condition, so again I1 Z1 is equivalent to I4 Z4, okay, or I1 I2 Z2 is equivalent to this current is same, I2 is equal to I4. So, this is equivalent to E divided by Z1 Z4. Similarly, here the current I1 is equivalent to I3. So, it means that is equivalent to E by Z1 plus Z3. So, by solving these these equations, we can find out, by solving this E by this and simplifying this, we will get that Z1 Z2 is plus Z1 Z4 is equal to Z1 Z2 plus Z2 Z3. So, this Z1 Z4 Z1 Z2 is cancelled out. So, it will be Z1 Z4 is equal to Z2 Z3, but it is in the complex form because here we are using AC components. So, because of the AC component there is two terms, one is magnitude and other is the angle of the phase angle of the instrument. So, this product of impedance, so we know that the product of impedance of opposite arms must equal to the product of impedance of the another pair of opposite arms. So, here two conditions should be fulfilled. One is the magnitude of opposite arms should be equivalent, and the second is the phase angle, because it is a complex impedance. So, phase angle should be should also be equal. So, from above equation we can write there is Z1 Z4 is equal to Z2 Z3. So, Z1 theta 1 angle theta 1 Z4 theta 4 is equivalent to Z2 theta 2 into Z3 theta 3. So, we can segregate it. So, here Z1 Z4 is equal to, the angle will be added. So, Z1 Z4 is equal to theta 1 plus theta 4 is equivalent to Z2 Z3 and angle theta 2 theta 3. So, for the balance condition two criteria should be fulfilled. One is the magnitude criteria, that is the Z1 Z4 is equivalent to Z2 Z3, and second is the phase criteria, that is theta 1 plus theta 4 is equivalent to theta 2 plus theta 3. So, this is the two conditions for the AC bridges to be in balance state. So, there is one example of AC bridge that there is an impedance Z1 is equal Z1 Z2 is given, Z1 Z2 and Z3 is given, and we have to find out Z4. So, again we have to find out the magnitude and the angle of the Z4. So, for finding the magnitude, simply we will apply this formula Z4 Z1 Z4 is equal to Z2 Z3. So, Z4 is equal to Z2 Z3 by Z1. So, by this we can find out that the value of Z4 is 1 kilo ohm, but again we have to find out the angle of theta 4. So, theta 4, again this is the balance condition, phase balance condition, theta 1 plus theta 4 is equal to theta 2 plus theta 3. So, this balance condition, so from there we can find out theta 4 is equal to this, substituting the value we will find out that the value of theta 4 is minus 50 degree. So, it means ki theta 4 minus 50 degree means ki this impedance Z4 is basically a capacitive element, okay, and possibly in the series capacitance. Similarly, one more numerical is here, that whether we have to find out whether the bridge is in balance condition or the unbalanced condition. So, simply again the two conditions should be fulfilled, one is the magnitude balance condition, another is the phase balance condition. So, as we see in this equation that Z1 Z4 is equal to 20 kilo ohm and Z2 Z3 is also equivalent to 20 kilo ohm. So, it means the Z1 Z4 is equivalent to Z2 Z3. So, the magnitude is in balance condition. Now, we have to find out whether the phase balance is there or not. So, in phase balance condition the Z theta 1 plus theta 4 should be equivalent to theta 2 plus theta 3. So, here we find out that theta 1 plus theta 4 is equal to 70 degree, but theta 2 plus theta 3 is equal to 80 degree. So, this phase balance is not there. So, it means the bridge is not in the balance condition. What are the different application of AC bridges? As we know, in AC bridges we can measure the value of inductance, resistance, we can measure the value of frequency when suppose we have designed a oscillator for a particular frequency, then we can check whether the frequency generated by the oscillator is same for what we have designed it or not. We can also use it for the phase shifting or the filtration purpose, and it is also used for the measure of the frequency of audio signals and so many type of applications of AC bridges. So, there are different type of errors in AC bridges because we are using capacitance, inductance and AC sources. So, there are so many errors because of the stray capacitance or the eddy current losses and the electrostatic, electromagnetic losses are there. So, one is the stray conductance effect. So, in stray conductance effect, if no proper insulation is done between the various component of the bridges, so this error will cause because of the leakage current from one arm to the another. So, and this type is basically this type of error happens when we are using high impedance bridges. So, to overcome this error, the apparatus should be mounted on a insulating stand. Similarly, in eddy current errors are basically in the standard resistors and inductance change the bridge values that cause the error, and to reduce this error, the material with large conductive masses should not be placed near the bridge. Second is electrostatic coupling. When there is a capacitance, then electrostatic coupling is there, and because of that the electrostatic loss is there. So, similarly, the error due to electromagnetic coupling. So, electromagnetic coupling, the source and detector, the EMF is induced in detector directly. There is residual error and there is frequency error. So, frequency error means if vibration in sinusoidal waveform or other, so there is a frequency error. So, there are two basic components that we have used, one is capacitor and the inductors. So, capacitors with high resistance dielectrics are represented by series RC circuit, capacitors with low dielectric resistance are represented by parallel RC circuit. And we know capacitor is basically when a dielectric material is sandwiched between the two conducting plate, then the capacitor is formed. And the capacitance reactance is generally capacitance reactance is inversely proportional to the frequency. It means ki when frequency increases, the reactance of the capacitance will decrease. So, when we represent the capacitance in series form, then it is Rs plus Cs, and when we can represent is in the parallel form also. So, capacitance which have high resistance dielectrics, that we will represent in series form, otherwise in shunt form. So, in series impedance we know that Zs is equal to Rs, basically Zs is equal to Rs plus Xs. So, that means when we place Xs is equal to Rs plus 1 by j omega Cs. So, by multiplying j in numerator and denominator we will get this value. Similarly, here Yp is equal to 1 by Rp plus 1 by X. So, by placing this value we will get this equation. Similarly, dissipation factor, the quality of capacitor is expressed in the form of dissipation, and for the parallel circuit the equivalent is dissipation is Xp by Rp, and for the series circuit it is Rs by Xs. Similarly, inductance are also used, and in AC bridges we have to measure, we can measure the value of inductances. So, in inductances again we can represent it in series combination or the shunt combination. So, inductors when there is a pure inductance, then we can represent it because it has some resistance value in the coil. So, it is represented by series resistances. So, Q factor, that is the quality factor of the inductance. So, again when we represent inductance in series form, then the quality factor Q is equal to Xs by Rs, and that is equivalent to omega Ls by Rs. Similarly, if we represent in parallel circuit, then it is Rp by Xp, and that is equivalent to Rp by omega Lp. So, in this I will discuss two type of bridges, normal bridges that is used. One is the capacitance comparison bridge, and other is the inductance comparison bridge. So, in capacitance comparison bridge, unknown capacitance is measured with the known capacitance. So, here the unknown capacitance, suppose Z1 is the unknown capacitance, and we have to measure it with in comparison with the this Z2. So, suppose in this circuit the two arms have a variable resistance, and in one arm this is the unknown resistance Zs, and it is shown in series resistance, series combination. Then there is a one capacitance, a known capacitance, known standard capacitance, and then there is a variable resistance. So, again we know that in series combination this Z1 is equal to R1 plus J by omega c. Similarly, Z2 is equal to, also because this is also in series. So, Rs plus minus this one, Z3 Z4 is equal to R3 R4. So, under the balance condition we know that Z1 Z4 is equal to Z2 Z3. Now, placing the values of Z1 Z4 Z2 Z3, we find this equation, and then by solving this equation we will get R1 R4 minus J R4 by J by omega C1 is equal to Rs R3 minus J R3 omega by omega C3. Now, equating the real and imaginary part, means separating the real and imaginary part, we will get the value of R1 R4 is equal to Rs R3. So, here Rs is equal to R1 R4 by R3, and similarly by comparing the imaginary terms we will find out the value of Cs. So, here Cs is equal to C1 R3 by R4. So, the advantage of this type of bridge is that there is no component, means neither the value of Rs nor the value of Cs depends on the frequency. So, that the value will not change if there is change in frequency occurs. Then again we can measure a parallel capacitance combination. Suppose a capacitance is shown in the parallel combination with the resistance. So, to measure that capacitance value, we have to place a parallel resistance capacitance combination in the bridge. So, suppose here is Cp and Rp is the capacitance whose value we want to measure, and there is the known standard capacitance C1 and Z1. So, we have to vary the Z1, and again we can write the Y1 is equal to, Y1 is the admittance, that is equivalent to 1 by Z1. So, that is equal to 1 by R1 plus J omega C1. Yp again the known capacitance 1 by Z2 is equal to 1 by Rp plus J omega Cp. Z3 and Z4 are the pure resistances. So, by varying Z3, Z4 or Z1 we can find the balance condition, and under the balance condition we know that Z1 Z4 is equal to Z2 Z3. So, by placing the values of Z1 Z4 Z2 Z3 and segregating the real and imaginary terms, we find out the value of Cp and Rp. So, here Rp is equal to R1 R4 by R3 and Cp is equal to C1 R3 by R4. So, again in this we can see that in this equation there is no component of frequency. So, again there is if there is any variation in the supply frequency or anything, then it will not affect the values of the components. So, inductance comparison bridge. So, here the inductance comparison bridge is shown. So, inductance comparison bridge, basically the inductance in series is compared with the inductance in series. So, again the bridge is balance condition Z1 Z4 is equal to Z2 Z3. So, by placing the value of Z1 Z2 and separating the real and imaginary terms, we have to find out the value of Rx and Lx. Again here these components are frequency independent. So, this is all from my side in this lecture. Thank you.